Welcome back. In previous video, we come to know about how can we get any desired odd periodic function just by superimposing various sine waves, and we called it as Fourier sine series. But to create a desired odd periodic function, we must know proper frequencies of superposing sine waves. To get these frequencies, we used Fourier sine transformation. Along with this, we came to know about Fourier cosine series and Fourier cosine transform. Okay then, in this video, let's go a step ahead and let's try to get an idea about Fourier series, Fourier transform and Laplace transform. Well, to start with, I am going to consider Fourier sine series and Fourier cosine series. Remember that Fourier sine series can be used only for odd functions, and Fourier cosine series only for even functions. Okay then, what if we combine these two so that we can apply it for any functions without bothering about whether it is odd or even? And we call it as Fourier series. Here we can get any resultant functions just by superimposing many sine and cosine functions without worrying about whether they are odd or even. Then what about frequencies? Well, as usual, we will get them from Fourier transformation. Just observe that we simply combined Fourier sine series and Fourier cosine series to get Fourier series, right? In a similar way, we can get Fourier transformation by combining Fourier sine transform and Fourier cosine transform. To make it too elegant, let's join a minus iota to sine transform and then let's add them. Then we get this expression, right? But we know that cos of omega t minus I sine of omega t can be written as exponential of minus I omega t, which is called as Euler's formula. And this result is called as Fourier transformation. But why do we use a complex term there? Well, there are plenty of uses. First one, it makes maths easier because it's always easier to deal with exponentials rather than sines and cosines, especially while dealing with integration. Second, it opens many more ways of opportunities so that we can apply this Fourier series and transformation. Well, let me explain this by taking an example. We know that we can create any periodic function by using Fourier series, right? But have you observed that these functions were never able to return to their original position? They always grow in the same direction, right? Then definitely we cannot create such functions or images by using Fourier series. Well, can we create such functions or images if we use complex term or Euler function? Yes, of course, we can. But before coming to know how, let's have a look at this Euler's function. We know that any complex number can be denoted by z is equal to x plus iy, where x is a real part and y is an imaginary part. And also we know that it can be written as z is equal to r e power I theta. Just for simplicity, let this r be 1. Then it can be rewritten as z is equal to cos theta plus I sin theta. Then comparing these two equations, we will get x is equal to cos theta and y is equal to sin theta. Okay, let's plot them and let's see what will be the resultant. Look at that. The resultant is a circle, and since we have taken r is equal to 1, it will be a unit circle. But it is revolving in a clockwise direction, and in physics we call it as negative direction. So to get a positive direction, let's change the sign of sine function, then let's see what will happen. See, we get anti-clockwise rotation, which is a positive direction for us. Thus, to get anti-clockwise rotation, we use e power minus I theta instead of e power I theta. Similarly, we will use e power minus I omega t instead of e power I omega t in our Fourier transformation equation. Well, then we came to know that using Euler's function in Fourier transform, we are actually getting frequencies of circular motion. But in previous video, we used pendulums, right? In previous video, we combined pendulums to create any function. Similarly, we can attach these circles to create any function, just like this one and this one and this one too. Well, to create these functions which will return to their initial positions, we used Euler's formula. But can they create previous functions which will never return to their initial positions? Yes, it can. Just watch this. Then how it is possible? Nothing. Simply by taking time axis into the consideration, this is possible. While saying about Euler's function, I showed you that it creates a circle. But observe that I haven't taken any time axis there, right? If I take time axis into account, it won't be a circle. Instead, it will be a spiral. And if you look the spiral from one side, it looks like a circle. And if you look from another side, it will be a sinusoidal wave. Thus, inclusion of Euler's function gives us more opportunities because it has more wider range. And just by changing the way of getting results, we can get any desired function. And this is the power of Fourier transformation. However, this Fourier transform doesn't include any type of damping. That is, it doesn't include any functions which will decay eventually or grow eventually. For these to include, along with Euler's function, let's join e power minus alpha t, where alpha is greater than 0 and is called as damping factor. Then e power minus alpha t into e power minus I omega t becomes e power minus of alpha plus I omega into t, and let alpha plus I omega be is equal to s. Then it becomes e power minus st, and Fourier transformation becomes Laplace transformation.